Hello friends, welcome to the next lecture in the series Cosmological Perturbation Theory. In the last few lectures we looked at perturbation in various types of tensors. We looked at tensor of rank 02, perturbation in tensor of rank 02, perturbation in tensor of rank 11. We looked at perturbations in scalar, perturbations in a vector physical quantity. We derived the general expression and then looked at the various components. For example, for a tensor of rank 02, we looked at 00 component, 0i component, which is same as I0, and then we looked at ij component. So let us now look at perturbation in a very popular rank 2 tensor. When what we are interested in is that the various types of tensors, scalars and vectors which we have studied in standard cosmology. We would like to see that how those tensors, scalars and vectors transform from one gauge to another gauge. So let's start with the one such tensor quantity, which is the metric tensor. So we would like to study perturbations in the metric tensor. The perturbed metric can be written as G mu nu is equal to its G mu nu bar, which is the background value, plus delta G mu nu is perturbation in the gauge in which we are studying G mu nu. So G mu nu is the value in perturbed gauge. G mu nu is a value in some perturbed gauge. G mu nu bar is the value in background gauge, and this delta G mu is the perturbation to the background value, and this perturbation is in this gauge in which G mu nu is in which the value is value of this metric tensor is G mu nu. So we have perturbed gauge, background and perturbation, and remember that perturbation is a function of eta xi, or you can say it's function of x alpha, where x alpha is the coordinates of the background gauge. So perturbations, and all of this we have studied in the previous lectures. We have looked at various examples of all the perturbation transformations. So this lives on the background FRW metric on the FRW coordinate system. This is the FRW value in FRW system. This is in a perturbed gauge. Now we have seen in standard model of cosmology that G bar mu nu is equal to A square eta mu nu, where eta mu nu is the Minkowski space-time metric. It's a diagonal metric with the 00 coordinate with the 00 value -1, and xx value like 11 value is 1, 22 value is 1, 33 value is 1. So this is Minkowski metric, diagonal metric -1, 1, 1, 1, and when you multiply by A square, this becomes the FRW metric. Now we can write this delta G mu nu when we can write this as A square H mu nu. What is H mu nu? H mu nu is basically all the elements of delta G mu nu when you divide them by A square. So all the elements you divide by A square, you will get H mu nu. So delta G mu nu is A square plus some perturbed metric H mu nu, some metric H mu nu, and when we put it here, this becomes G mu nu in perturbed space is equal to A square eta mu nu in Minkowski eta mu nu, which is Minkowski space-time metric, plus H mu nu. Now, if you look at this expression, you can easily see that what is G bar mu nu in FRW space, in G bar mu nu in FRW space time is A square eta mu nu. But now instead of eta, when we are looking at G mu nu in perturbed gauge, instead of eta, we have eta mu nu plus H mu nu. So eta mu nu, which is the value in FRW system, becomes eta mu nu plus H mu nu. So you can say H mu nu is perturbation in eta mu nu. H mu nu is perturbation in eta mu nu. A square H mu nu is perturbation in G bar mu nu. So G bar mu nu perturbation value is equal to A square eta mu nu. Eta mu nu perturbation value is equal to H mu nu. Okay, so now what we are interested in is we would like to see how what is the value of G with mu nu indices on top. This is G mu nu rank tensor of rank 0 to. Now we would like to see how does this expression look like in a like if we write G this as a tensor of rank 20, that is G mu nu on top. How does this expression will change if we write G with mu nu on top? So this is what we want to find. What is this equal to? Now, before we find an expression for this, let us recap a few things about this the background metric and the Minkowski space-time metric. So, if you this background metric in FRW system, you have this multiplied by this. You can write and this is alpha. So this we know from the standard model of cosmology that this is equal to delta nu mu, and if we write it like this G then this is equal to 1. So this is a review of the relationships which we have looked at in the standard model of cosmology, and what else? We also know that in Minkowski space-time, we have this relationship, and the way this g mu nu is designed, what we want this g mu nu is, we want this g mu nu also to obey this relationship, that we want g mu nu to obey this relationship. We want g mu nu So g mu nu in the perturbed metric will also obey the same relationship. Where's the same relationship? And also this is equal to 1. So this is what we know so far. This is FRW, this is Minkowski, and this is what we want. We want a perturbed metric to obey this relationship. So starting with this knowledge, now we are going to construct this thing. Oh my God. This is Mathematica. Sometimes it's so funny. This is what I want. G mu nu is equal to what? Okay, now let us look at this expression. Before going further, I have increased the size of the font so that it looks better on the video. Okay, now coming back to this expression. Okay. Now we can start with the we want to find this guy G mu nu. Now, if you remember from general relativity or from standard or the first course in cosmology, standard model of cosmology, that this is equal to is equal to this. Just to keep the font consistent. So this is what we know from our previous knowledge, that this is equal to a square eta mu nu. And also, if you remember, this is equal to this. So the inverse matrix of G mu nu is equal to this. So in the, let me write this in the FRW. This is perturbed and this is in the FRW. In the FRW system, G bar mu nu is equal to one over a square eta mu nu, and this is basically the inverse of this matrix. So when you take reciprocal of all the elements of G mu nu, you get this. And remember that the matrix elements of this are same as the matrix elements of this in Minkowski space. So you have in Minkowski metric is -1 1 1 1. When you take reciprocal, you again get -1 1 1 1. Here in FRW you have a square -1 1 1, and when you take reciprocal you get the diagonal matrix 1 over a square -1 1 1. So yeah, and if you like, I can copy this here. So FRW metric is this, and just keep the font consistent. Do both are Times New Roman, but why is one different from other? This is Times New Roman. This is Times New Roman. Okay. Now I think it will be okay. No. Anyways, so yeah, so when you multiply this with this, you get 1. Now in the perturbed metric, we have this relationship, we have this relationship, we have this relationship, and now we would like to find what is this guy inverse of G mu nu equal to. This is what we want to find. Inverse of G mu nu, we can write this as G plus this guy, yeah, plus delta of this, delta of this. So we have this relationship and this relationship. Now our goal is to find this guy. we want to find this guy and this guy. Okay, so this is what we know, and from here, how do we come here? Let us use this information. Let's write this as G mu alpha, G mu alpha, delta G mu alpha, and this can be written as alpha alpha. Now let us multiply both. When we multiply both, what do we get on left hand side? Multiply these two equations. So on left hand side, we multiply G mu alpha, G alpha nu, and we get this guy, delta mu nu. Right hand side, when this is multiplied by this, we get delta mu nu. When this is multiplied by this, we get this multiplied by this. So this, and then we have this multiplied by this. And then we have this multiplied by this. So this multiplied by this is a second order term, and in linear perturbation theory we keep only first order terms. We will drop all the second order terms. So this multiplied by this we can drop, and we are left with this. Now here this cancels this, and then we are left with this is equal to minus of this. Okay, so what is this? G bar mu alpha is this. Let's copy this. G bar alpha nu is G bar is this. This guy is this. This. And this is alpha. Alpha. And this mu alpha is this. Alpha. And this delta G is this multiplied by a square. this alpha multiplied by a square. This. So now we have this is equal to this cancels this, and we have this here. So on the left hand side, we can write this as one second. On the right hand side, I can write this as this. Now eta mu alpha is acting upon H alpha nu, and note that H alpha nu is this H mu nu is perturbation in Minkowski spacetime. A square H mu nu is perturbation in FRW spacetime, but H mu nu is a perturbation in Minkowski spacetime. So if you have to raise and lower the index of H mu nu, you will be using the Minkowski spacetime metric. So this is very important, and I will put it in formula sheet also. H mu nu, let me make a note here so that I don't forget to put it in formula sheet. H mu nu is perturbation is perturbation in the Minkowski spacetime, which is therefore to raise therefore use eta mu nu or this. To raise and lower the indices of this nu and this H mu nu on top. So we will use this metric to raise and lower indices of h mu nu, because h mu nu is perturbation to the Minkowski spacetime. It lives on the Minkowski spacetime. Delta g mu nu lives on FRW spacetime, is perturbation in the Minkowski spacetime. You can say h mu nu lives on, it lives on spacetime. Lives on the Minkowski spacetime. Okay, so when you look at this expression, alpha contracts, so this will be equal to, right hand side is equal to, when alpha contracts, this becomes mu. So this is right hand side equal to. Sorry, alpha contract, this will be h, this guy, mu top, nu at the bottom, 1 1 1 1 metric. So this becomes this. Now on the, I can raise nu, I can bring nu to top if I multiply it by nu alpha. If I multiply this by alpha, what I want to do, I want to bring nu to top. Right, if I want to bring nu to top, so I can contract this with, I think this should work, or this should be nu. Yeah, this should work. Like this. Now let us see, what do we get? This guy is equal to 1. So this is 1. And this guy is equal to, we are using eta nu alpha is acting on h bar mu nu. It's acting on h bar mu nu. And it will, when nu contracts, it will raise the index, and we will get this on right hand side. We will get nu contract, and here we will get h mu alpha. This. Okay, so we have found that delta g mu alpha can be written like this. The inverse of this, inverse of this guy, g mu nu, this inverse of this is this. So we have delta g mu nu, this guy is this guy, is this, and this guy is this. Therefore, this guy G bar mu alpha is this, and this guy is this. This, and this guy is this. Therefore, we can write this as this minus this. And if you like, you can replace alpha with nu. This. So the inverse of perturbation is delta G mu nu, and its inverse is this. And if this is a square h mu nu, this is minus 1 over a square h mu nu. I will put this expression in the formula sheet. All the relevant equations from here I will put in the formula sheet. Okay, thank you for watching this video. See you next time.